Welcome back to Cosmos in a Pod, Space and Astronomy series. Today, we're taking a deep dive into a realm of the universe that's both captivating and crucial to understanding how everything well is. Dwarf galaxies. You know those seemingly insignificant little guys, often overshadowed by their dazzling larger galaxy siblings?
Yeah, it's fascinating how often the universe's biggest clues hide in the smallest places, isn't it? Dwarf galaxies are like those tiny puzzle pieces that hold the key to understanding the whole picture.
Exactly. They're like the cosmic underdogs, quietly revealing secrets about the universe's grand design. So to kick things off, help us visualize this. What exactly are we talking about when we say dwarf galaxy? What sets them apart from the spiral giants we're more familiar with?
Well, imagine you're shrinking down the Milky Way, our own majestic spiral galaxy, taking away most of its stars until you're left with a fainter, more compact structure. That's essentially what a dwarf galaxy is, a smaller, dimmer version of the galaxies we typically picture.
Okay, I'm picturing a mini Milky Way but with fewer stars. How much smaller are we talking here?
We're talking millions or even billions of stars, which sounds like a lot, but pales in comparison to the hundreds of billions found in a spiral galaxy like the Milky Way. And in terms of size, they're significantly more compact, spanning less than 10,000 light years across.
So they're like the mini metropolises compared to the sprawling gigacities of the universe. Does their size make them hard to find?
Absolutely. Their smaller size and lower star count make them much fainter, so they can be incredibly difficult to spot against the backdrop of the cosmos.
That makes sense. Now, you mentioned shrinking down the Milky Way, which is a spiral galaxy. Are all dwarf galaxies spiral-shaped too?
Not at all. One of the most exciting things about dwarf galaxies is their diversity. We have dwarf ellipticals, which are older and smoother, resembling fuzzy spherical blobs. Then there are dwarf irregulars, the rebels of the bunch, still actively forming stars with chaotic, less defined structures. And we can't forget the dwarf spheroidals, the faintest of them all, almost like ghostly whispers in the vastness of space.
Okay, so we've got smooth and spherical, chaotic and star-forming and faint and ghostly. What a range. How do astronomers even begin to classify these cosmic oddballs?
Well, the classification is based on their morphology, which is just a fancy way of saying their shape and structure. But what's really fascinating is what these different types tell us about the evolution of galaxies.
Ooh, I'm all ears. Tell me more about that evolutionary connection.
Imagine the early universe, just a billion years after the Big Bang. Everything's still in its infancy, and these dwarf galaxies might have been some of the earliest structures to emerge from the cosmic chaos.
So they're like the universe's first drafts, the building blocks from which larger galaxies were formed.
Precisely. Think of it like this. You start with these smaller, simpler dwarf galaxies, and over billions of years they collide and merge, eventually forming the grand spiral and elliptical galaxies we see today.
That's incredible. So those faint little dwarf spheroidals might hold clues to the universe's very beginnings.
They just might. And their stories don't end there. They also hold clues to one of the biggest mysteries in astrophysics: dark matter.
Dark matter, always a crowd pleaser. Why are dwarf galaxies particularly useful for studying this elusive substance?
Because they're thought to be dominated by it. In fact, the ratio of dark matter to visible matter in dwarf galaxies is much higher than in larger galaxies.
Okay, so they're like little dark matter havens. But how do we even know dark matter is there if we can't see it?
That's the beauty of it. We can't see dark matter directly, but we can infer its presence through its gravitational effects on visible matter like stars.
So by observing how stars behave within these dwarf galaxies, we can learn something about the invisible hand of dark matter that's shaping their movements.
Exactly. And that's where it gets really interesting. It turns out that the way stars move in some dwarf galaxies doesn't quite match up with what our current models of dark matter predict.
Ooh, a cosmic mystery. What kind of discrepancies are we talking about?
For example, our models suggest that there should be many more small, faint dwarf galaxies than we actually observe. It's like there are missing puzzle pieces in the cosmic inventory.
So there are dwarf galaxies lurking out there that we haven't found yet. That's mind-boggling.
And there are other discrepancies too, like the way dark matter seems to be distributed within these dwarf galaxies. It's not quite behaving as our models predicted.
So these tiny galaxies are already challenging our understanding of dark matter. That's amazing.
Yeah.
They're like little rebels shaking up our cosmic understanding.
They certainly are. And that's just the tip of the iceberg. There's so much more to uncover about these fascinating objects.
Well, I'm officially hooked. Dwarf galaxies. Small in size, but huge in cosmic significance. Who knew?
Exactly. And we're just getting started. There's a whole universe of knowledge waiting to be unlocked within these intriguing cosmic entities. It's like these dwarf galaxies are holding up a cosmic mirror reflecting back at us the gaps in our understanding.
It's incredible how something seemingly insignificant can challenge our fundamental understanding of the universe. Now, you mentioned these discrepancies between what our models predict and what we actually observe in dwarf galaxies, particularly when it comes to dark matter. Can you unpack that a bit more? What are some of the leading theories trying to explain these differences?
Well, the prevailing theory about dark matter, the lambda cold dark matter model, posits that dark matter particles are cold, meaning they move slowly and they don't interact much with each other or with regular matter. It's like they're gliding through the universe in their own lane, only interacting through gravity.
Just like cosmic ghosts passing through walls.
A good analogy. However, this model struggles to explain certain observations we see in dwarf galaxies. Take the missing satellites problem, for instance. The lambda cold dark matter model predicts a much larger number of smaller, fainter dwarf galaxies than we've actually detected.
So like there are missing dwarf galaxy puzzle pieces that should be out there, but we haven't found them yet. What are some of the explanations for this missing satellite problem?
There are a few intriguing possibilities. One is that these missing dwarf galaxies are actually out there, but they're so faint that our current telescopes just can't detect them. Another possibility is that our understanding of galaxy formation, particularly in the early universe, is incomplete. Maybe something prevents these smaller dwarf galaxies from forming in the first place.
So we might be missing something fundamental about how these early galaxies came together.
Precisely. And then there's another puzzling observation, the core cusp problem. The lambda cold dark matter model predicts that dark matter density should be highest at the center of a galaxy, gradually decreasing outward, forming a cuspy profile.
Like a pointy hat on the dark matter halo.
Exactly. But observations of some dwarf galaxies show something different. They reveal a more evenly distributed dark matter density at the center, creating a core more like a flat top hill.
So the dark matter isn't behaving as we expected.
Right. This mismatch has prompted scientists to explore alternative theories about dark matter. One such theory is the self-interacting dark matter model. This theory suggests that dark matter particles actually can interact with each other, unlike the traditional non-interacting view.
So maybe those cosmic ghosts can bump into each other after all.
Exactly. If dark matter can interact, it could potentially explain some of the discrepancies we're seeing. For instance, self-interacting dark matter could smooth out the dark matter distribution at the centers of galaxies, leading to those observed cores.
It's incredible how these tiny galaxies are prompting us to rethink our understanding of something as fundamental as dark matter. Are there any other alternative theories gaining traction in the scientific community?
There are. One particularly intriguing contender is warm dark matter. Unlike cold dark matter, which moves slowly, warm dark matter particles would have moved at higher speeds in the early universe.
So less like cosmic ghosts and more like cosmic race cars.
A fun way to put it. This difference in speed could affect the formation of structures in the early universe, potentially explaining the missing satellites problem. If dark matter moved faster, it might have prevented smaller dwarf galaxies from clumping together in the first place.
So it's like the fast-moving dark matter smoothed out the cosmic landscape, preventing smaller structures from forming.
That's the idea. However, both warm dark matter and self-interacting dark matter are still very much in the theoretical realm. There's a lot more research to be done before we can definitively say which model, if any, accurately describes the true nature of dark matter.
It's like we're piecing together a cosmic jigsaw puzzle, and these dwarf galaxies are providing some crucial but often perplexing pieces.
And the puzzle is far from complete. There are so many other unanswered questions about dwarf galaxies that keep astronomers up at night. For instance, why do some dwarf galaxies stop forming stars altogether?
That's a good question. What are some of hypotheses about why star formation might cease in these galaxies?
Well, one possibility is that larger galaxies, like our own Milky Way, can strip away the gas from smaller dwarf galaxies as they pass by, essentially cutting off their fuel for star formation.
Like a cosmic bully stealing their lunch money.
A rather dramatic analogy, but essentially. Another possibility is internal processes within the dwarf galaxies themselves, like powerful supernova explosions. These stellar blasts can heat up and expel gas from the galaxy, effectively halting star formation.
So it's a battle between external forces and internal dynamics that determine a dwarf galaxy's fate.
Exactly. And then there's the question of the role dwarf galaxies played in the reionization of the universe. Remember that period when the universe transitioned from a fog of neutral hydrogen to a clear, transparent state?
Yes, like the universe clearing its throat after the Big Bang.
That's a great way to put it. While the first stars and massive galaxies likely played a major role in reionization, some scientists believe that dwarf galaxies with their early formation and abundance might have contributed significantly to this process as well.
So these little guys might have been instrumental in shaping the universe as we know it.
It's a possibility that's actively being investigated. And as we continue to study dwarf galaxies, we might uncover even more surprises about their role in cosmic evolution.
It's like we're constantly revising the story of the universe, and these dwarf galaxies are adding fascinating new chapters. Are there any specific examples of dwarf galaxies that have particularly surprised or intrigued astronomers?
Oh, absolutely. There's a whole cast of characters out there. Take the large and small Magellanic Clouds, for instance. These two dwarf galaxies are visible to the naked eye from the southern hemisphere, looking like detached pieces of the Milky Way.
I've heard of those. Aren't they our closest galactic neighbors?
Indeed. They're orbiting the Milky Way and are close enough that we can study them in great detail. The Large Magellanic Cloud is particularly interesting because it's a hotbed of star formation bursting with vibrant nebulae and star clusters.
So it's like a cosmic fireworks display, constantly creating new stars.
Exactly. It even boasts the Tarantula Nebula, one of the most active star-forming regions in our local group of galaxies.
Wow, that's incredible. What about the Small Magellanic Cloud? Does it have any standout features?
Well, the Small Magellanic Cloud has been heavily influenced by the Milky Way's gravity. In fact, it's being slowly pulled apart, leaving a stream of gas and stars trailing behind it like a cosmic kite with a long tail.
It's amazing how these interactions between galaxies can create such stunning structures.
And speaking of interactions, another intriguing dwarf galaxy is the Sagittarius Dwarf Spheroidal Galaxy.
I remember you mentioning this one earlier. It's the one being devoured by the Milky Way, right?
That's right. The Sagittarius dwarf is currently passing through the Milky Way's outer halo, and its stars are being slowly stripped away by our galaxy's gravitational pull.
So it's like a slow-motion cosmic collision playing out over millions of years.
Exactly. It's a fascinating example of how larger galaxies can grow by consuming smaller galaxies, a process known as galactic cannibalism.
Galactic cannibalism. Now, that's a metal name for a cosmic phenomenon.
Right. And the Sagittarius dwarf isn't the only one suffering this fate. The Milky Way has likely gobbled up many dwarf galaxies over its lifetime, and it continues to do so today.
So the Milky Way is built on the remnants of its smaller, less fortunate neighbors.
You could say that. And studying these remnants can help us understand how our own galaxy has evolved over billions of years.
It's incredible to think that the history of the Milky Way is intertwined with the fate of these smaller dwarf galaxies.
Absolutely. And it's a reminder that the universe is a dynamic and ever-changing place where even seemingly insignificant objects can have a profound impact on the grand cosmic tapestry.
It's mind-blowing to think about the Milky Way engaging in this cosmic ballet of destruction and creation, shaping itself through these interactions. It really highlights the dynamic nature of the universe.
It's a beautiful dance of gravity and matter, constantly reshaping the cosmic landscape. And speaking of reshaping, we can't forget the role dwarf galaxies might have played in one of the most transformative events in the early universe: reionization.
Right, you mentioned reionization earlier. It's like the universe flipping a switch and going from opaque to transparent, right?
Exactly. In the early universe, shortly after the Big Bang, everything was a hot, dense soup of particles. As the universe expanded and cooled, these particles combined to form neutral hydrogen atoms, creating a thick fog that shrouded the cosmos.
So the universe went from a particle soup to a hydrogen fog. What a visual. What happened next?
Well, as the first stars and galaxies ignited, their intense radiation began to strip electrons from the neutral hydrogen atoms, a process called ionization. This ionization gradually transformed the opaque fog into a transparent universe, allowing light to travel freely for the first time.
So it's like the universe went from being shrouded in darkness to suddenly bursting into light.
Yeah.
And you're saying the dwarf galaxies might have played a part in this cosmic illumination.
That's one of the leading hypotheses. While the first stars and massive galaxies certainly played a major role, some scientists believe that the sheer abundance of dwarf galaxies in the early universe meant their radiation could have contributed significantly to reionization.
So these little guys might have been punching above their weight, helping to clear the cosmic fog and pave the way for the universe we see today.
It's a possibility that's actively being researched. And if it's true, it paints a fascinating picture of these dwarf galaxies as unsung heroes of cosmic evolution.
It's amazing how much we're still learning about these seemingly insignificant objects. What are some of the key questions that astronomers are still trying to answer about dwarf galaxies?
Well, one of the biggest mysteries is how the very first dwarf galaxies formed in the early universe. Were they shaped primarily by dark matter, or did other forces and processes play a role?
It's mind-boggling to think about those early stages of the universe when everything was just starting to come together. What other mysteries are keeping astronomers busy?
We're still trying to fully understand the mechanisms that drive star formation in dwarf galaxies. Why do some dwarf galaxies burst with star formation while others seem to have shut down completely? Is it due to interactions with larger galaxies, internal processes like supernova feedback, or a combination of factors?
So it's a complex interplay of forces that determines the fate of these galaxies and their ability to create new stars.
Exactly. And then there's the ongoing quest to unravel the true nature of dark matter. Dwarf galaxies, with their high dark matter content, continue to provide us with valuable data that could help us refine our models and potentially unlock the secrets of this elusive substance.
It's like every new discovery about dwarf galaxies opens up a whole new set of questions, pushing us further down the rabbit hole of cosmic exploration.
And that's what makes astronomy so exciting. It's a never-ending journey of discovery, and these dwarf galaxies are proving to be some of the most intriguing destinations along the way.
They're like hidden treasure chests, just waiting for us to unlock their secrets. It makes you wonder what other cosmic surprises might be lurking out there in the vastness of space.
Absolutely. The universe is full of wonders, and as we continue to explore, I have no doubt that dwarf galaxies will continue to surprise and amaze us, revealing new insights into the grand cosmic narrative.
Well, I, for one, am eager to see what the future holds for dwarf galaxy research. They might be small, but they've certainly left a big impact on our understanding of the universe. And that's it for this deep dive into the fascinating world of dwarf galaxies. If you want to keep exploring the cosmos with us, be sure to follow and subscribe to Cosmos in a Pod and check out our YouTube channel for even more cosmic adventures. Until next time, keep wondering and keep exploring.